Okay, good morning, everyone. If it's morning by you, or good other part of the day for all of those who it's not morning for. Um, this is the Axom tutorial that's part of the HPC IC, High Performance Computing Innovation Center's HPC tutorials. Um, Axom is part of an umbrella of software projects that are on um, Lawrence Livermore's open source Radius suite. There have been several tutorials in the series already um, that are almost all relevant to Axom. So Axom uses BLT as its build system. That's the build, link, and test. CMake foundations. We use SPAC for building our dependencies or third-party libraries that Axom depends on. We use Caliper and Adioc for annotating regions of code that we want to capture performance on and capturing metadata. Raja is our um, abstraction library for running kernels on host and device in different computing spaces. Umpire is our memory abstraction for um, being able to allocate and copy and deallocate memory in different memory spaces. And then we use MFEM, which is a tutorial that's coming up next week when we process high order meshes. It's a high order finite element library. And we use Flux for allocating things in various HPC clusters. So what is Axom? Axom is, let me get the exact sentence we used. Axom is our computer science infrastructure components for high performance computing applications. So we provide computer science infrastructure for physics simulations and other high performance computing suites. So we started this project about 8 years ago, and when we were starting a new physics simulation code, a next-gen physics simulation code, and we have several existing simulation codes at Lawrence Livermore. Each of them are pretty large, consisting of like millions of lines of code developed by dozens of people over tens of years. And there's a lot of good computer science infrastructure in these libraries. But the way we've developed things in the past is that um, the infrastructure was sort of part of the simulation tools, and it wasn't sort of independently tested, and each library maintained its own copy of uh, its computer science infrastructure, and these things varied slightly between things. So when we were starting up this new code, we decided, let's have a library that contains a lot of this shared common computer science infrastructure for handling things like logging and checkpoints and restarts and data stores to keep the fields and other metadata associated with running our application all in the same place, as well as things like computational geometry, which is sort of shared between libraries and has a lot of historical knowledge on like corner cases and edge cases that um, people spend a lot of time debugging these things and sort of each code independently maintain their own copies of these things. So the idea was, let's create a library that has a lot of this shared computer science infrastructure. Since it's dedicated to infrastructure, we could use best practices in developing the code. We could independently test each feature on its own using unit tests. And then we could share a lot of ideas with the other code. So sort of take best practices from a lot of our codes, develop it inside this new library called Axom, and then develop it for our simulation codes and sort of share all of this good stuff with other codes. And then over time, we've gotten contributions from the various codes when they need a new feature, and then it helps other codes. And it's also been used in various open source projects. So we get contributions from people outside of Livermore. It's a good venue for our summer interns to develop software. It's sort of easy to get into. We have a lot of documentation. So this is our main page on GitHub. This is our README. So we have our documentation here, axom.read the docs. And yeah, so this is our tutorial. Let me click here. So this tutorial is sort of a set of utilities that we have incorporated into Axom that uses a good portion of the components in Axom. So it's sort of a good place to talk about the various components of Axom and how they work together. The actual application that we're going to talk about is a computational geometry problem. We have triangle meshes that we read in, and one of the requirements for our applications is that the triangle mesh that we read in is a watertight surface. It bounds a volume, there's no gaps, and there's no self-intersections in the triangles. So we developed this component that given a point in space is able to tell if it's inside or outside of a triangle mesh. And one of the first things that happened was we got users who just found triangle meshes online, just searching Google, and the meshes they found were really bad. So it had lots of gaps. It had lots of components that intersected and triangles that intersected. This is actually the example that one of our users found right away. It's like a Matchbox car model of, I think it's a Porsche, but it was just a file that some user found online and started using, and the code crashed. So we decided to build up a utility that we called Mesh Tester, which reads in this triangle mesh in a format called STL, which is a common format for triangle meshes. And we load in this triangle mesh. We check if any of the triangles are degenerate, meaning that it doesn't have three independent points. It's either 3 points that are collinear or 3 points that are identical. And so it gets rid of all these degenerate triangles, and then it checks for self-intersections between the triangles. So I'll go through all of these lessons as we go along, but essentially we're building up some of the capabilities of this mesh tester utility and using it as a way of seeing what's in Axom. I guess before I get started, does anyone have any questions? There are also, this is a tutorial. We're going to look at code. We're sharing links with people that gives you a development environment inside Visual Studio Code, VS Code. So have link for tutorial. Thank you, Burl. So the tutorial is based here, posting to the chat. Thanks, Burl. Any other questions? Christy, before we get started sort of going through the tutorial, did everyone get links, or is there a link to like the sign up page for the Google spreadsheet that we could post?
Yeah, so I can get that link again. But I did send out an email earlier this morning with this exact link to a Google form where you can send in your email so that we can give you an AWS instance.
Okay, perfect.
Yeah, and if you haven't gotten one yet or you would like to get one, um, yeah, put your email on there and we're keeping track of, who's got one, who hasn't, and we can send one out to you.
Okay, perfect. Thank you, Christy.
Yeah.
Also, I just wanted to mention, I don't think people are able to unmute themselves in this, in the way we set up this tutorial, but if you do have questions, you could raise your hand and we could unmute you, or you could post questions to the chat, and there's a bunch of people that are signed up, the ones in the panelist thing on top that are looking at the chat and trying to answer questions as they come along. That's a great question. How long are the instances available for practice after the course? Christy, I think we've left them open for like an hour or so after the course usually. Is that
Yeah, typically an hour or two um, after the tutorial so that you can kind of play around with things is what we go for. Um,
perfect? And if
yeah.
people wanted to sort of like use sort of these workspaces afterwards, is it something that they could like start up their own instance and sort of work on these things? Do we have a way of doing that? Like with a
Um,
pre-built environment?
I don't think people are able to launch the instances themselves. We would have to launch one for you.
I see.
Um, yeah, but if you reach out to either myself or Brian, we can help you with that. Um,
Okay, perfect. So if people are interested in having this sort of environment afterwards, reach out to us and we could see if we can make that happen. Excellent. Any other questions before I go into things? Thanks. Brad just posted instructions for how to build Axom. So that's on our read the docs. Okay, excellent. So one more comment about the AWS instances. I think we set them because this tutorial goes through building this mesh tester, but then um, as we iterate on it, we're going to add other computational spaces using Raja. So part of this uses OpenMP and part of this uses GPUs. The instance we're providing has several cores. I think it's like 4 CPU cores, but it also has one GPU on it. So we're going to be like running code with GPUs and seeing speed ups and things like that. Okay, any other questions before I get into it? If you do have questions, then please post them and I'll try to address them. Okay, so Axom tutorial. So we're building up this mesh tester application. The way this tutorial is structured, I didn't give sort of independent time for people to sort of work through things and sort of add pieces. The idea is I'm sort of guiding you through parts of Axom that are used, and then you could investigate things later and run the applications and make changes and things like that. So it's mostly me going through this tutorial, not people working independently. But if anyone on this call has comments or thoughts or suggestions about ways they might want to see a tutorial on Axum after we're done, I would love to hear them, and our team would love to hear them. So with that in mind, let's just sort of review what we're going to do and then get into it. So we're building up this mesh tester application. Uh, we have um, a set of applications that build on top of an installed Axum. So we have Axum that's installed and we're going to use it, not develop parts of Axum, but sort of use Axum in developing a new application. Our first lesson sort of talks a little bit about Axum and then builds the simplest possible application with Axum. We call Axum about, which tells us which components are in Axum. Then we introduced this STL triangle mesh format, which is a common format for triangle meshes, and we read it in and print out how many triangles are in the mesh and log some things to standard out. We then build our first application that goes through the triangles in the mesh and checks against every other triangle to see if those two triangles self-intersect. We're going to use a function that checks if two triangles intersect. We're not going to build up that function in this tutorial, but it'll give you pointers to where that is and how those sorts of things are defined. Then we're going to see that that naive algorithm is fairly slow for large triangle meshes because it has every triangle check every other triangle. So then our first idea is to just port this to Raja, do a big for all loop that runs our checks on device or with OpenMP or sequentially, and then we could see the relative performance of these things. And then that will still be reasonably slow because that has O of n squared runtime. Every triangle checks every other triangle. And our final lesson is to use a spatial index to filter out the things that could not possibly intersect using cheap proxy tests, checking bounding boxes. And then once we filter those out, we could do the actual hard computational geometry intersecting two triangles. And we'll see that that's a way faster algorithm, both on the CPU and on the GPU. So with that in mind, let's dig into it. So lesson 0. So in this lesson, we're going to build an application using Axom. Axom uses the FMT library for string formatting. That's an external library. So it's something that became part of the standard, I think in C++20, and more of its features are getting in C++23 as standard print and standard format. So that might look new to people or might be something they're using all the time. It essentially makes formatted strings look sort of like they do in Python in C++. So Axom has a bunch of dependencies that we could build against. Conduit is required for several of Axom's components. Conduit is a library that has key value pairs, hierarchical key value pairs. And it's a way of manipulating data and sharing it easily. We have a tutorial coming up next week on Tuesday morning that talks about Ascent, which is built on top of Conduit, and that will give you a good background into Conduit as well. So please come back for that tutorial on Tuesday morning if you're interested in more about Conduit. The MFM library is an optional dependency if we're dealing with high order meshes. That also has a tutorial coming up. Raja and Umpire had a tutorial last Thursday, I believe. And I'm sorry, Tuesday, yes, 2 days ago. And I think that was recorded. So if you're interested in that, Tuesday this week, thanks, Rich. If you're interested in that, you can get that recording or click on links and follow that. Those are optional dependencies that deal with running well on hosts and device. So performance portability. Raja deals with running kernels, launching and running kernels on a host or device or different spaces, computational spaces. Umpire deals with moving memory around. And BLT is a build system that originally was Axom's build system, and then other codes wanted to use it, so we made it its own library, and there's also a tutorial on that was part of this series. Okay, so I guess the first thing we'll do, I wonder if I could pull this out into a different window. I think that will work. Could someone confirm that you can see both of these windows at the same time, please? Yes. Okay. Excellent. And is part of my window obscured? I have like the chat open, so I'm just gonna move things around so it's not in my way. Okay, that should probably be good. Okay, so um, I think I opened it to a different file than the default. So let me go to the directory everyone's in. So if you're running this tutorial, like if you're running on this cloud thing, you should be in this radius tutorial directory. And okay, perfect. Is the font big enough for people to see, or should I try to make it bigger? Could someone?
It would be better if it was bigger.
That's what I was thinking. Thanks, Brad. I think there's a way to do that. I'm going to see if Control Plus works. Oh, it does. Okay, excellent. Is that good? Okay. How do you get to the shell pane? I hit Control and the key on my keyboard that has like tilde on it. Okay, hopefully, if that doesn't work for people, they can still ask questions. Eric, you said bigger, please. Is this big enough, or did I get that already? Okay. Oh, it was good. Okay, well, I'll make it smaller if I don't have enough screen space. Can someone please help Peter with an AWS instance? Okay, excellent. So back here. Okay, so the first thing we're going to do is build our tutorial. Um, so uh, our our build system is CMake based, and because we build on multiple platforms, CPU-based platforms, GPU-based platforms, local laptops, commodity supercomputers, advanced supercomputers. Axom uses something that we call a host config to maintain a lot of the CMake variables so that we could just sort of use them uh, without having to define a lot of things on the command line. So you could define all of these variables on the command line, but typically we just sort of pass these in. So when we built Axom, when we configured Axom and installed it, we gave paths to all of the libraries we depend on and put them in this file. So, okay, so what are we going to do? We're in the radius tutorial folder. We're following this little script right here. We're going to make a build directory, make dir build, and then go into it. And then we're going to call CMake to configure our space. So we call CMake. We point it to this host config file that we're looking at up here. And then we have to tell it to use the release build type. And then we tell it that the source directory is one directory up. So we're going to configure it right now. Yeah, so if you're following along on this script, one change is that this didn't include the CMake build type, so please make sure that you're building in release mode. Otherwise, if it's in debug mode, you'll find that it runs slower than you might want it to. Um, so please configure it in release mode. Also, the instances we're using, I think, have 4 CPU cores. So if you're passing in a J flag to your make command, please make sure to use J4. And I checked this yesterday, but let me just see. If I do nproc, it'll tell me 4. And if I do NVIDIA SMI, it'll tell me that I have an NVIDIA card on here with a Tesla T4 chip. I think I did that to just get it in one line. So NVIDIA SMI-L tells me there's one NVIDIA thing. What was the full CMake flag? This was the full CMake flag right here. So if you look in the hostconfig.cmake file, I put it in right there. Excellent. Okay, so we are in our build directory. We just configured CMake. So the next thing we do after that is we build it. I'm going to use the 4 CPUs that we had. So this will take a couple of seconds because it has to build against CUDA and things like that. So this lesson has 5 directories in it, which turn into 5 applications, lesson 0, 1, 2, 3, 4. It's going to build each of those. BLT comes with some unit tests built in that we call smoke tests. So it builds a couple of extra unit tests that we call smoke tests that check that BLT is configured properly. If we're using MPI, it checks that MPI is configured properly. Similarly for CUDA, we have some sort of very simple CUDA executables that just make sure our CUDA environment's right, or same for OpenMP. And if we're using gtest, which Axom uses for its unit tests, there's also a smoke test that just checks that we have gtest set up correctly. We could ignore this warning. Sometimes CUDA gives warnings about about functions that we've annotated as host and device. Those can be hard to get rid of. We've tried to get rid of a lot of them, but some of them still are in there. While we're waiting for this to build, does anyone have any questions? Or if anyone's following along, are they also building or having trouble with that? If you are, please ask questions in the chat and we'll try to answer them and get you going. This seems to be almost done. Okay, so while that's building, let's look at our CMake file just to see what we're actually building. So we are building the Radius tutorial project. This is the line that brings in BLT. Okay, could someone please help Pradeep? If you give some more details, we could help you with that. Please paste the full command. Yes. So we started in the Radius tutorial directory. Oh, I lost it. Hold on 1 second. This was the command. Thanks, Cyrus. So that's the command. We started in the Radius tutorial directory. We created a subdirectory for our build directory. We went into that and we called CMake. We pointed to the host config and we use CMake build type equals release. Yes, and please omit the greater than symbol when you run it. Okay, so let me do that. Okay, so this is our CMake lists file. When we're using BLT, the host config provided a path to BLT. It should be BLT sourcedir. I don't see it yet, but I'm sure I will in a second. There we go. So we provided a variable that tells us where BLT is available within our build. It's in our Axom repo. Source. So that gives us a function we call to set up BLT. Typically, we set some variables beforehand to configure things. Then we call setup BLT, and it gives us a bunch of macros, and it sets up like the right languages and things like that. Okay, thanks. Could someone share the AWS instance link with Arun also, please? Okay, so for this example, we also had to pass in a path to the installed Axom. That's axomdir. So that's this CMake file assumes we're passing in a valid Axom. Once we have that, we could say find dependency Axom, and that takes the installation export from Axom and sets it up with all of its third-party libraries. And then once we have that, there's a bunch of tutorials, a bunch of macros in BLT to help you set up your targets. Probably one of the most useful ones are BLT add library, which adds on to CMake's add library and does some extra things, and BLT add executable, which adds on to CMake's add executable and adds some things. So to set up our target with all of the third-party dependencies we care about, all of the include paths, all of the other things, we say BLT add executable. It BLT handles setting up targets that are compatible with CUDA and with OpenMP and with MPI if we're building with those things, as well as HIP if we're on AMD platforms and want to build with that. So to add our executable, we give it a name, we give it the source path, and we give it the dependencies. In this case, the dependencies are Axom, some of its built-in things, FMT and CLI 11. I'll talk about those. And if we're using OpenMP, CUDA, or HIP, we add those using this BLT list append, which is a conditional add if things apply. So we add these executables. 0, 1, and 2 are always on. 3 and 4 are on if we're building against Raja and Umpire. And then I set this up so that there are unit tests for all the lessons. So just to, now that we've built, I'm just going to run ctest to just make sure everything is set up the right way before I start this tutorial, so we don't have any hiccups along the way. So we have as few hiccups as possible along the way. I ran ctest-n to just list all the tests, and now I'm going to run them with ctest-j4. So it's running in parallel with 4 MPI rings. It's going to run the sequential, the OpenMP, and the CUDA tests, as well as these smoke tests that I was talking about before. Let me just run one of those smoke tests manually. BLT, which one should I run? I'll run the MPI smoke test. So this is, oh no, what did I do? Probably has the word smoke in there. BLT MPI smoke. So I typed in the wrong thing. So this just checks that MPI is working properly. So it runs MPI with 4 ranks, and it says, I'm expecting there to be 4 ranks, and in fact there were, so I passed the test. So that's a really useful way just to check that everything's configured the right way before we get started. Okay, so let's go into lesson 0 and look at it. Let's see, I'm back on this on the left. So, okay, now we actually have our C++ file. It's lesson zero. Lesson zero's check Axom configuration. If you're following in the folder, it's under radius tutorial, lesson zero, check Axom configuration. This is about as simple as things get. We include Axom's include files. Here we have config.hpp, which has a bunch of the compile defines associated with Axom. It sort of tells us which components are available and things like that. We include each of Axom's components have a header file that includes all of the files associated with that component, just for convenience. We could include them one at a time, but it tends to be pretty convenient to just say we want to use the Axom core component and include that. I'll talk about the components in a minute after we go through this thing. So, and we're using the FMT library for string formatting. So this is just our simple file. We have some sort of cout statement that just says we're checking the properties of Axom. We include this one thing called Axom get version here, which is just going to print out version info. And then we have another thing called Axom about that has just about statements, talking about our configuration. So let me run that. So let me show the bin directory first. So when we built that, it built 5 executables, lesson 0, 1, 2, 3, and 4 in this tutorial. And now we're going to run lesson 0, which tells us that we're using version 090 of Axom, and specifically, we're not on a release version of Axom. We're sort of building off the develop branch of Axom, which is using commit with SHA-58F99. That's at some point after Axom's 090 release. And then we print out some helpful information about our configuration. So we're using the C++ 14 standard. There's a type called Axom index type, and we're using a 32-bit thing for our Axom index type. It's an unsigned int that's 32 bits. You could configure Axom using a 64-bit, and that would have a size that's 8, because it's 8 bytes. This configuration of Axom has several programming models enabled. It has CUDA, MPI, and OpenMP. And we're building against the full Axom with all of its components, and this lists all the enabled components in alphabetical order. And then finally, we have a few built-in dependencies that this Axom is built against, as well as a few external dependencies that were built against. And I mentioned some of those briefly before. I realized I'm talking about Axom's components, and I didn't sort of list what they are. So I wanted to just take a minute and show you what those components are. So I'm going to Axom's documentation on Read the Docs. And I want to talk about this chart for a second, but let me answer Eric's question first. Oh, perfect segue into what I was about to say, Eric. So you're asking if the components are easily separable, or sort of how they work. So that was just what I was going to talk about. We have a bunch of Axom components. Some of them build on other components. We have the core. I think we had a one-line summary of these. Yeah. Okay, I'll just talk through them. But if you're interested in a one-line summary, you can go here. And if you want to see documentation about individual components, there's a user guide for each thing, which is sort of an overview, like a user-friendly overview of the component. And then there's also Doxygen source code documentation generation, which sort of tells you sort of at a lower level, at the source code level, what each function does. So the core component has a bunch of capabilities that are sort of common to all of Axom and just sort of generally useful. So there's some utilities for dealing with strings, things that aren't built into like the C++ standard library that are just useful for dealing with strings. There's things dealing with like file utilities, and a lot of Axom is set up to use either the host or device, to use CPUs or GPUs when available. And not all of the standard library is compatible with running on device. So a lot of the standard library functions aren't marked as host and device, so they can't run on the device. So we have some utilities that mimic the standard library utilities, like standard min and standard max, or what's a good example? If you look through it, you could see the types of things we provide. So that there's some utilities. We also have, we'll go into the tutorial later and see our usage of this, but we have a class called Axom Array, which is sort of our version of standard vector, but it works on host and device and can take memory allocators that are compatible with Umpire, so that we could use things like we could use APIs that look like standard vector on the host or device. So that's our Axom Array class. Okay, so built on top of that, we have some logging functionality. Slick is our logging component. It exposes a few macros that we're going to see in future lessons for printing out like info statements and debug statements and asserts and things like that. Lumberjack is a utility that allows you to deal with logging statements that are sort of sent out to all of our MPI ranks, and it deduplicates some of them. So instead of getting 1,000 messages that says, you know, a logging statement that everything prints, it sort of puts them together and it coalesces those into fewer logging statements. Moving up this list, Slam is a library that deals with sort of the low level operations of operating on a mesh. So it deals with, it's a set theoretic sort of framework. It deals with sets, relations between two sets, and maps, sort of functions on sets. It's another sort of low level core library within Axom. Mint is a higher level mesh library, mesh component that is similar to the VTK abstraction, if that means things to people. It's sort of a way of putting together sort of meshes that could be operated on. Multimat is a little specialized in a lot of our physics libraries. We deal with multiple materials, and multimat is a way of handling the bookkeeping for these multi-material data structures, which allows you to encode them densely or sparsely. Sometimes you only have materials in localized parts of the mesh, so it's sort of a bookkeeping library for that. Spin is our spatial indexing library, so it provides, I'll talk about this later in the tutorial, but it provides a way of indexing lots of spatial data so that you could ask questions and only get the parts of our geometry that are relevant to those questions. Before I move up to Quest, I'll move to the right. Primal is our computational geometry library. So it has primitives like bounding boxes and circles and spheres and Bezier curves and things like that, as well as operations on them. So you might want to know if two triangles intersect, and Primal has a function called intersect that takes two triangles and returns true or false. CIDR is our simulation data repository library. It handles hierarchical key value pairs. We use that for storing simulation data, meshes and fields and things like that, and exchanging them between various physics libraries. And it also has built-in capabilities to handle I/O, file output, things like checkpoints and restarts, and talking to other libraries. So it's a way of exposing simulation data um, in memory to other apps, and as well as via I/O. Inlet is built on top of CIDR and gives us a way of um, helping with parsing input to simulations. So a lot of times there's um, a lot of knobs and toggles that we want to set for a simulation, and inlet makes a way of creating tables that could give data to simulations. Clay is a library that deals with a library that deals with setting up multi-material simulations. Um, so it could be complicated to set up complicated geometry where you have different regions of a mesh with different materials, and they spatially relate to each other in interesting ways. So it handles setting up this geometry and dealing with which materials replace others. I'm not doing it justice because there's a lot of background here, but please check out the documentation if you're interested in that. And then finally, Quest sort of puts a lot of this stuff together. It handles sort of high-level queries, high-level spatial queries over meshes. Um, so it's sort of the type of question that involves complicated searches but can be expressed relatively easily a lot of times. So if you have a big surface mesh bounding a volume and you have a point in space and you want to know, is this point in space inside the contained volume or outside the contained volume? So it operates on a mesh. Usually there's a lot of query points or query objects, and it uses spatial indexes and stuff like that to give us to efficiently solve these questions. Is a point inside an object? If I have a mesh and a point, and I want to know which element is this point in, or yeah, it's mostly questions of that form. So it sort of uses a lot of the pieces of Axom. Okay, so now that we've done that, let's go back to our tutorial. We finished lesson 1, which runs a simple about application. We're going to move on to lesson 2. So if we're following in this tutorial, I'm sorry, that was lesson 0. We're moving on to lesson 1 now. So this is loading an STL mesh. So we talked about the various components of Axom. Just sort of as an aside, Axom uses the CLI11 library to deal with command line input. So that makes it easy to parse input. And I mentioned before that we have this slick component that deals with logging. I won't go into too much of the details, but we can configure slick using this. In this case, we're setting up a simple class to just sort of easily configure things and initialize a slick, and when we start it, and it finalizes slick when our logger goes out of scope. It's using, this class uses the RAII, resource acquisition is initialization. I think that's what that stands for. But it basically means we have a variable that's in scope and it calls the constructor. And then when that variable goes out of scope, it calls the destructor. So it's a way of managing memory pretty easily. So if we look at our example, I'm just going to the main at the bottom. It uses RAII, so we have this logger. It goes out of scope at the end, so we don't have to deal with that. Thanks, Rich. Yeah, so Rich just posted, I got it right. Resource acquisition is initialization. Okay, So um, Slick has a few different levels, so that the application can say, I want to see all the debug info. I might just be interested in seeing warnings and errors, let's say, so you can tell it what to do. I won't go into too much details about the CLII thing, the command line input, but it should look pretty familiar to people. You add options, um, as well as descriptions. One of the nice things is of that library, which is not developed by Axom, we just use it, is that you could add some checks to the command line options. Like if we pass in a file name, we want to make sure that the file actually exists. So instead of the code having to do it, it's sort of built into the library. Um, so where is the main part of this application? Yeah, I guess it's in this triangle mesh class. So basically, we're loading a triangle mesh in the STL format, and we're just providing very simple things. So going back to this tutorial on the left, this class just tells us how many triangles we have and is able to return a reference to the array of triangles. So it does very simple things. Here's the code that loads in the triangle mesh and converts it from sort of arrays in memory to instances of primals triangles. We have a one-liner, or maybe not a one-liner, but a couple lines to read in an STL mesh. We're just going to use that in this code. So we set the file name and then we read it. And then we go through that mesh, and for each, okay, so we have the triangle mesh has an array of triangles, so it's an Axom array of Axom primal triangle. And for each of these, we create a triangle instance and push it into our array. So let me just show you what that. So this Axom array essentially has the same API as standard vector. So whenever you see Axom array, think standard vector, but it's a standard vector that is intended to operate nicely with CPUs and GPUs in different spaces. Okay, so it's a very simple application. We create this triangle mesh, and then we just print out the number of triangles. So let's run that right now, see what happens. So it's been lesson 1. And if I just run it, we said that the input file is required. So it tells us, hey, wait a minute, that input file is required. You're missing it. This won't work. We also can have like -h, like help, to tell us if it's there or not. So I'm going to add my mesh. We created a folder called STL meshes. That's one directory up. That has a bunch of triangle meshes in the STL format and some other files in it. The one that we're going to use here is called sphere binary, and we're going to use -v for verbose mode. Oh, yeah, I forgot to mention, I just used some Slick statements here. So Slick info prints out an info message, Slick warning prints out a warning message, and Slick debug prints out a debug message. So that's what we're seeing here. We set it up to tell us info and warning. We are built in release mode, so the debug messages don't happen in this. They get filtered out in release mode. Okay, so what do? We read in an STL mesh, STL mesh sphere binary, and we parsed it, and then it tells us we have 1,280 triangles in this mesh, and that is all this application does. I guess this is a good point to show something else. So Axom, mostly for our internal testing, we have a data repository that has a bunch of, a data repo that contains a bunch of our testing files. But the feature that I wanted to show here is that GitHub has a built-in way of visualizing STL meshes. So I could show you what that mesh that we just looked at is. It's called sphere binary. It's an STL mesh. It's a triangle mesh. And hopefully no one's going to be surprised to find out that it's a triangle mesh of a sphere. The binary in there is because we're using the binary format of STL as opposed to the ASCII format. Okay, so before I move on, does anyone have any questions? Are people following along with the tutorial? Is it working for them? Can you load multicolor STL meshes? You can load multicolor STL meshes, but we're not doing anything with the color information. So just to give a little context on that question, STL meshes have geometry, like XYZ positions of every triangle, but they also have an attribute that people could use to give the triangles color or like sort of label the triangles. I don't know if GitHub's reader interprets those colors, but I guess it would be easy to check if we had a file that had multicolor. So I would personally ask ChatGPT if GitHub's reader supports it before checking it. But I guess to answer your question, I think Axom just ignores the color attribute in STL meshes. We could easily use that if there was a need to do that, but I don't think we've had that. So I guess, Andy, if that's of interest, please let us know and we could support that. Okay, going back to our tutorial. So we have a very simple application. It reads in a triangle mesh and it tells us how many triangles there are. For the next lesson, we're actually going to do something with this triangle mesh. So I'm sort of anticipating my tutorial. Sorry about that. So the STL format is a set of triangles. This is the ASCII format for a very simple tetrahedron, which has 4 triangles. It's the simplest shape in 3D. It's built out of 4 triangles. I think this will work. Let's see. Yeah, okay. So this shows you what that tetrahedron mesh is. 4 triangles. Okay, let's go back here. So STL is a common format. It's very widely used. One of the problems with this format is it provides your triangle mesh as a soup of triangles. That's how it's referred to. Basically, it doesn't tell you any connectivity information of those triangles. It just says, here's a triangle. It's defined by these 3 vertices. Here's another triangle. It's defined by these 3 vertices. You could prescribe the normals for the triangles, but you can't describe the connectivity of those triangles, how they relate to each other in STL. So effectively what that means is there's a lot of bad STL meshes out there because they're just lists of triangles and not every generator will put them in exactly the same place. There's also like weird floating point computational stuff where, different triangles might be intended to be identical, but actually are, just slightly off. So the first thing we do with STL meshes is typically to weld the triangles, which means all the vertices that are within some epsilon of each other sort of become the same. We sort of just move them to the same place to clean up the mesh a little. Because that's such a common utility, we provide a function to do that. So Axom quest weld triangle mesh vertices, tri-mesh vertices. It takes a mesh and a weld threshold, which is a number, and it welds them together. So let's see what that looks like. We're in lesson 2 now. So naive self-intersections. What should I point out here? So we're using a bunch of our Axom components here, core, slick, mint, primal, and quest. And it has that same parser and logging thing. We updated our triangle mesh class a little bit here. I guess the part I'm on in the tutorial is this welding thing, where we say Axom quest weld triangle mesh vertices. And then after welding, we tell you how many unique vertices there are and how many triangles there are in this mesh. Okay, so now that we've done that, let's talk a little bit about primal. It's our computational geometry primitives and operations. We have primitives like a point in space and a triangle and a bounding box. Sort of, so primal stuff is meant to be very low level and efficient. So a lot of primal is templated on the dimension and on the type. So a two-dimensional point has 2 coordinates, a three-dimensional point has 3 coordinates, rather than creating a point class that could be arbitrary dimensional. We template it to 2 or 3 because it's used sort of at the base of a lot of our computation, and we need it to be as efficient and fast as possible. So, so we have this, I guess I'm on this side here. We have this point class, triangle class, bounding box class. That's templated. We usually use type aliases just to make things look a little easier. So we'll say things like using bounding box type equals Axom primal bounding box double 3. So double is the coordinate type and 3 is the dimension. We also have a bunch of operations or operators in primal that take 2 primitives, like a bounding box and a bounding box, and tell you if they intersect. So that looks like primal intersect bounding box, and it returns true if they intersect and false if they don't. Similarly, so that function is overloaded. So intersect could take 2 triangles and return true or false. We also have things that could compute like bounding boxes. If you give us a triangle, it will give you the bounding box of that triangle as a primitive primal bounding box, which we could then use for further processing. So what do we do? Let's see. We're using an array of triangles here, an array of bounding boxes. This is the code that given an array of triangles, creates an array of bounding boxes of those triangles, and it also creates a single bounding box that contains the whole triangle mesh. So we're doing that in line. Axom array supports iterators, so you can just say for each triangle in triangle mesh.triangles, compute its bounding box and then place it in the triangle bounding boxes array, and then add that box to our sort of triangle mesh bounding box instance. So we're building up the bounding box of the triangle mesh, and we're building up bounding boxes of each triangle at the same time. So let's look at that in the code for a second. It's right here. And then once we have that, we just print out the bounding box of the triangle mesh. Similarly, I said before we wanted to check for triangles that are degenerate. So we do that here using the simple loop. We say for each triangle in that array, we're calling primal triangles internal degenerate function, which returns true if it's degenerate and false if it's not. And if it's degenerate, we push it into a list of degenerate triangles. We're later going to skip those when we do our intersections. So it's good to know ahead of time, if we have degeneracies and to skip them. Okay. Is that everything this does? No. So then, given all that background, we now have our very basic algorithm that checks, given a triangle mesh, um, as as well, which contains not only the triangle primitives, but also the bounding box primitives containing each triangle. Um, we loop through the triangles for each triangle. If it's degenerate, we skip it. Otherwise, we loop through all the triangles with greater index than our current triangle. We skip that one if it's degenerate. And otherwise, we call triangles intersect, index 1, index 2. So that's a helper lambda. I think we had that. Okay. So we pass in this triangles intersect lambda. This is sort of thinking ahead to how we work on the GPU. We're going to pass in lambdas to do this stuff for us. So let's look at that lambda, which is very simply defined here. Check intersect. We pass in two indexes. We use those indexes as indirection into the triangle array, and we call axom primal intersect on those two triangles. So this function is sort of an indirection thing. It given two triangle indices, it pulls out the actual geometry of the triangles at those indices and calls axom primal intersect on those two triangles and returns true or false. There's a couple of small details here of axom primal intersect. The first is include boundaries. So we set that to false because we don't want two triangles to say they're intersecting if they only intersect along edges of those triangles. We want to check if the interiors of those triangles intersect. And then there's this tolerance factor, which is something you could pass in at the command line, but essentially it says um, it makes the triangles a little fuzzy because computational geometry is in sort of floating point. A lot of it uses fuzzy geometry, not exact geometry. So it sort of gives it a little bit of a threshold, and we say, if we slightly extend them and they intersect, or slightly pull them in a little and they intersect. So that just gives us a little bit of a tolerance. And then that's our whole application. So let me run that. This one is lesson 2. And we're going to do it on that same mesh. So STL meshes, sphere binary. And I forgot what other parameters I have. So let me do -h. Okay, so we could pass in different welding thresholds. That's like how far points need to be before we consider them distinct. And then intersection threshold has to do with how far triangles are before we consider them intersecting. So if we don't pass in an extra parameter, it checks our triangle mesh. It says reading triangle mesh, loading the mesh took this long, welding the vertices took that long. This is how many vertices and triangles we have after we weld it. It has 0 degenerate triangles, and its bounding box is from -5, -5, -5 to +5, 5, 5. And computing the intersections took 0.03 seconds, and it had 0 intersecting pairs. We could run that again using the use bounding boxes flag. And it should run a little faster. So what that does is, let me just check this. Okay, so I skipped over a detail. We have 2 lambdas. That's why I defined it with lambdas. So one lambda was directly call axom primal intersect on 2 triangles for every intersection. And then the other lambda was, let's do something a little smarter. Computational geometry on 2 triangles has a lot of weird cases we need to check. It's a lot more complicated to see if two triangles intersect than it is to see if their bounding boxes intersect. And that's sort of a common thing we do with computational geometry, where we could use proxy things to filter out candidates. So we know that two triangles can never intersect if their bounding boxes don't intersect. So this one does something a little smarter than the other one, which is if the two triangles intersect, if their bounding boxes intersect, and then if they intersect. So this uses short circuiting to say if their bounding boxes don't intersect, then just return false without doing the more expensive thing. And that was why we used that lambda to allow us to toggle between the use bounding boxes and not. Let me just show a slightly more complicated example. Instead of using the sphere binary mesh, I'm going to use the plain simp problem.stl. So this is a triangle mesh that's sort of a model of an airplane. I think I can do wireframe. Yeah. So I think this mesh has about 30,000 triangles, and we modified it. I think you can see it here. We modified it slightly to add some problems, some triangles that intersect. So this one's sort of like artificially generated. I don't know if it's easy to see. Let me go back. So we added this triangle here that intersects a bunch of other triangles just to artificially create a problem. And if I run this test, naive self-intersections, STL mesh sphere. Oh, I didn't change the parameter, did I? So let me just do that quickly. Plain simp problem. And the reason it's plain simp is because we have a more complicated plane model that has an order of magnitude more triangles. We have one with 300,000 triangles. Okay, so I'm calling this plain simp problems.stl. I'm going to add the -v flag for verbose mode because it's going to go a little slow. And this just, oh, actually in release mode, it's fast enough. So this one tells a, here, let me rerun that without the V so we see what's happening. Basically, that loads the mesh, welds the vertices. Stop that, it's distracting. Loads the mesh, checks for degeneracies, finds the bounding box of that mesh, checks for all the self-intersections, and tells us that there are 5 self-intersecting pairs. We saw that when I ran in verbose mode, it actually tells us what those intersecting triangles are. So with the bounding box check, it took 1.5 seconds, 1.55 seconds. And if I don't use the bounding boxes, it'll take longer. This is just running on a single CPU right now. Yeah, so that took 20 seconds to check every triangle using the triangle-triangle intersection. So adding that filter, checking the bounding boxes, turned out to be really helpful because it was basically, more than 10 times faster. Okay, so that was lesson 2, loading a triangle mesh using a naive self-intersection algorithm. We saw that even for a small triangle mesh, it could be expensive. There are filters we could apply to make it faster, but it still could be slow for larger meshes. I'm not going to run much larger meshes on this example, but I guess you could see that the mesh with like 1,000 triangles took, 0.05 seconds, so a couple milliseconds, whereas the one with 30,000 triangles took more than a second, even with our use bounding boxes. So our next step is going to be, okay, so this ran slow on the CPU. Can we make it faster by porting it to other models, porting it to OpenMP, porting it to CUDA. Instead of using raw OpenMP or raw CUDA, we're going to use the Raja library to do that, which is an abstraction that has a bunch of different backends in it. Before I do that, are there any questions that people want to ask that they haven't asked yet? I see the chat is fairly active. Okay, well, if you do have questions, please ask them along the way, especially if you're having trouble building the application. Hopefully we've worked past that for people who are following along. But definitely ask if you have questions. Okay, so now we're on lesson 3. We're going to still use our naive self-intersection algorithm, but we're porting it to Raja so we could run it in different models, OpenMP or CUDA. If we're on a machine that has HIP, like AMD hardware, this example would work with HIP as well. Can I share the command to run the last example? Sure. The one that ran on the sphere mesh was that. And then the one, oops, and then the one that ran on the plain simple problems mesh was, nope, that didn't go. Was that. And just as a reminder before I move on, so I'm in the build directory of our tutorials. If I look up a directory, there's an STL meshes directory. And if I show you what's in there, we have a bunch of different models. A lot of them, most of them are STL meshes, which we're concerned with in this tutorial. We were looking at the plain simp problems mesh. If you look at the plain simp mesh, it's the same thing, but we don't have that artificial problem, so there should be 0 self-intersections there. We also looked at the sphere binary and sphere file and tetrahedron file. Those are reasonably small. If I do, let's see, ls, that can work. Yeah, so if I show you the size of these things, we could see that the plane model is a lot bigger. That has like 300,000 triangles. That was our original airplane model that I didn't show. But then we have this Porsche model, which is like one of our car models that had problems that I showed on the previous page. And then there's also this file called car.stl, which has about 2 million triangles. We're going to look at that one at the end and see that it could run pretty fast with our eventual algorithm. Any other questions? Okay, if you do, ask them along the way. Okay, so now we're on the device. This example requires Raja and umpire support. Those are built into our container. We've also configured it with OpenMP as well as GPU support through CUDA. So our previous algorithm just used like a nested for loop. So just C++ for loop over each index, and then an inner loop over each index that's greater than the one we checked, and called our lambda, which checked intersections directly. And in this next example, we are modifying our algorithm. Okay, so this one is very similar to the previous one. It's the naive find intersections, but this time we pass in an execution space. So what are these execution spaces? Those are sort of tags that tell us where we're running. We could run sequentially that's on the host using a single core. We could run with OMP, OpenMP, that's using threads, using multiple cores. And we could also run with CUDA. That would be on the device, on our Tesla that's on this image. I think I need to update the tutorial. I modified this a little, so it's not in there just yet. But I'm going to show the command line for this. So lesson 3, if I do -H. So this one takes a new flag called policy, -P, policy. And we could set that to CUDA, OMP, or sequential, either using the strings, quote CUDA for CUDA, or their associated numbers in the enum, 0, 1, and 2 for CUDA, sequential, and OpenMP. CUDA, OpenMP, and sequential, 2, 1, 0. So this gives us a runtime flag that lets us control where we're running this on devices, on nodes that have various backends. We could choose which one to run it on. So yeah, it will look pretty similar. I just wanted to add this, that since we're controlling this at runtime, but we're calling something that's templated and compiled in, we need a switch statement to take our enum and turn that into templated code. So basically we switch on our policy flag, and if it's OpenMP, then we call naive find intersections with OpenMP. If it's CUDA, we call it with CUDA, and if it's sequential, we call it with sequential. The code changed a little since this tutorial. I need to update it because we were previously using like an explicit enum for this stuff, and after we created this, we realized a lot of users of Axom were using very similar logic to pass in these different enum flags, and we simplified that a bit. So instead of creating our own custom enum and ways of printing it out and dealing with it, we created this Axom runtime policy class. Let me just show that quickly. So that is in Axom's source directory. And again, I'm looking at a different directory than the one that was built in. You're sort of looking at a subdirectory called radius tutorial. And if you go up to the root of your container, there's also a directory called Axom repo. And that contains Axom source code. So you can look through that also. So it's Axom source, Axom core, execution, runtime policy. So if we look at that, it basically has what's in that tutorial, but it has an enum class called policy that has sequential, OpenMP, CUDA, and HIP. Those get compiled in when we have those available, and they're compiled out if we're not. So if you call a class that's not available, it won't compile. And there's just very simple ways of turning the string seq into the enum, as well as the other way to convert from the enum value into the string. So it's mostly just usability stuff. Okay, back to device self intersection. Okay, so the main thing to show here is what did we have to change to get this working with Raja? So here's where we have some complications in terms of like dealing with memory space. So if we're running on a device, we need to move all of our memory onto the device. So we load our triangle mesh into our CPU memory, our host memory. And if we're using a device, we have to move it onto the device. So we use Umpire to actually do this stuff, Umpire allocators. We have a host allocator, that's Umpire host, as well as a device allocator, which is Umpire device. The slight complication here is Not every build of this file will have a device. So if we're building in a configuration that doesn't have CUDA, then we just want to use our host device for this kernel allocator. So that's why there's this ternary operator here. It's if we're running on device, then we're using umpire resource device. Otherwise, we're just using the built-in allocator for our space. And then this code is is somewhat complicated here because we're managing between the host and device sort of manually here. So we have a triangle, we have a reference to our array of triangles, trimesh.triangles, and then we either move it to the device or if we don't have a device, we just create like an empty array for that. And then the extra concept that I haven't explained yet is that we have this Axom array class. It's compatible with hosts and devices, but when we actually call our kernels that use this array, we want to take away the ability to dynamically change the size of the array and some other functions that relate to like changing the memory, because our array doesn't support dynamic allocations, or there's limited support for dynamic allocations on device. So instead of actually passing in our Axom array, we pass in a class called ArrayView, which is sort of a view into the space of that array. It has a very similar API to Axom array or standard vector, but it takes away functions that modify the space. So there's no more pushback or clear or emplace back or things like that. So when we actually operate on these arrays inside of a kernel, we use an array view, not the array itself. And there's a very nice helper function in array to return the view. Essentially, it's a pointer into the data of the array as well as the size of the array, and some functions to work on it without changing the memory. So with that in mind, our kernel actually looks very similar. Okay, so we didn't change the loop that checks if it's degenerate or not. That's just on the host, because that was fast enough. And then here is what our modified thing looks like. So we still have a Lambda called triangles intersect. We sort of simplified those two and put them together. So here we either use bounding boxes or not. So it combines those two kernels together. If we're using bounding boxes, then we want to check if the bounding boxes intersect, or we just check if the triangles intersect. So this Lambda looks very similar. We just combined it into one. And then here is our kernel that is Rajified. So I guess I want to explain one last thing. Our previous one just had a nested loop through the triangle array and checked every pair of triangles. This next one is going to do the same, but because we want to take the results and return them to the user, we have to create space for those results. So we're actually going to do the loop twice. The first time we're going to count how many intersections there are, and then the second time we're actually going to go through those intersections and copy the indices of those intersections back. So this first one counts it. We're using a Raja reduce sum. So that's a reduction variable that just computes the count of the number of intersections. So it starts at 0 and it uses atomics. So this is the first one. We say Raja kernel, go over the columns and the rows, and if the row is less than the column, because we don't want to get 2 intersections for every intersection, so we're only going to check the ones that are where the second index is greater than the first one. And the triangles intersect using our lambda. Then we use this atomic to increase the number of intersections. And then once we have that, we could actually go through again, and for each intersection, we could add them to our result, which is our like intersections array. And then we could print them out to the user. So was that clear? Instead of going through once and just directly finding those intersections, we go through twice this time. First, we count the number of intersections and then allocate enough space to return that result, and then go through again and return it. So let's run this on some examples. We're going to give it the same STL mesh plain simp problems. And what other variables do we have? We have a policy. We're going to use bounding boxes. And we're going to use, first we're going to use the sequential policy. This one is actually going to run twice as long because we're running it on the CPU. And we're first checking to see if there are intersections, and then we're computing those intersections. But we could run that same thing with OpenMP on 4 threads. So this took 6.89 seconds. If we run it again with OpenMP, that took 3 seconds. And then we could run it with CUDA, and that took 0.4 seconds. So if we're running it on the GPU, it's a lot faster. But let's run this with a larger mesh now and see what happens. So instead of running with plain simp, we're going to run with the Porsche model. So the Porsche model has 150,000 triangles, and it ran in about 3 seconds on CUDA. But if we run it with OpenMP, it's going to take a bit longer. So basically what we've done so far is we took our naive algorithm that was a nested for loop. It had n squared, O of n squared computational complexity. And we just said, oh, GPUs are fast. Let's port it to a GPU, the exact algorithm. Here we're running with 4 threads, but it's still taking a long time. If it takes like more than 5 more seconds, I'll just stop it. You can see it's taking a long time. Yeah, okay, I'll stop it. But it turns out that it's not always sufficient to just port our nested for loops directly to GPUs. Maybe there's a smarter algorithm. Maybe there's something better we could do. So that leads into our 4th lesson. I guess before I jump into the 4th lesson, are there any questions? Okay, well, if anyone does have questions, please ask them in the chat. Okay, so this is our 4th lesson. Instead of just checking every triangle against every other triangle, let me go back to this figure that was here, this car. So the basic idea here is this triangle right here, like something in this, sort of headlight region, is very far from this triangle in like the wheel region. So we're still doing sort of complicated things to check if 2 triangles intersect. We're still checking, even with our extra bounding box test, we're still checking if bounding boxes intersect. That's a lot of work because this triangle here, I forgot what we said this mesh had. I think it was 150,000 triangles. So this triangle here has a lot of work to do to compare to, on the order of 100,000 other triangles, even if it's just checking bounding boxes, when, there's not many triangles that it's actually close to that it could intersect. So we could filter out a lot of these things sort of at the outset and not actually have to worry about that work. So, GPUs are great at doing computations. You could throw lots of things at them. They'll do, millions of things at the same time, give you an answer, make it faster. We saw that in this example with the Porsche model, it took, I thought it took 0.4 seconds before. Maybe that was a different mesh. Okay, so it took about, 3 seconds, 3, 4 seconds, even on the GPU to do this stuff. Um, but there's got to, if I run this with a larger mesh, so instead of Porsche.stl, I'm going to run it with car while I'm talking, and you'll see that that takes longer. So this mesh has like 2 million triangles. So then there's on the order of a billion things it needs to check here because it's 2 million. Okay, that was fun. It ran out of memory. I wasn't expecting that. Okay. Um, so I'm going to run that again on example 4 before explaining what example 4 is doing. So this is loading our mesh with 2 million triangles using a spatial index. And it was able to do that, computing all the intersections in half a second instead of crashing. But if I ran that on the Porsche model, which took like 3 seconds before, now instead of taking 3 seconds, it takes 0.3 seconds, 0.269. So we're able to filter out a lot of the work using a spatial index. So let me go into the details a little and then wrap up this tutorial. Okay, so instead of sort of naively going through every pair of triangles, we're going to use a spatial index to filter things. Axom has a BVH tree built in that operates on CPUs and OpenMP and CUDA, so it operates on all of the spaces we operate on, and HIP as well. The basic idea is you give it a collection of objects as well as the bounding boxes of those objects, and it builds up a tree of the overlapping bounding boxes. So when you give it a query, it goes down that tree and only gets the candidates that that interfere in some way with the thing that you're searching for, but it filters out a lot of things along the way. So instead of every triangle having a linear amount of work in the size of the triangle mesh, instead of checking n triangles against every triangle, the tree has sort of a logarithmic thing. It checks like log n other triangles, on the order of log n, and filters away the other things. So the runtime is a lot better of this algorithm because we're using this tree. So how do we use this tree? It's in the spin component. Spin is our spatial index component. It's a BVH tree. You tell it the index space that you're operating over and the dimensions. We set our umpire allocator for when it creates arrays and stuff. And then we initialize it with the collection of bounding boxes of our triangles. So that's, let me see if I could find this here. BVH. Am I in the wrong? I'm in the wrong one. Okay, let's try that again. BVH. Okay, so find intersections BVH. Here we go. We create a BVH tree, we set its allocator, and we initialize it. If you're looking at these timers, timer start, timer stop, those are basically just for interacting with the application, seeing how long things take. Axom has a built-in timer class. It uses C++'s timer behind the scenes. Okay, so how does this work? We load up our tree with its bounding boxes. It initializes the tree. It builds up this hierarchy. And then because we're checking the intersections of triangles against other triangles, we give it a batch query of the bounding boxes of all the triangles that we're testing. And it gives us for each input triangle, what are the possible intersections it could have? What are the indexes of the other triangles it could possibly intersect with based on overlapping bounding boxes? Here's sort of a detail. Because we're operating on either host or device, and we're returning sort of arbitrary numbers of entities for each input. We give it this like CSR sort of representation, compressed row storage sort of thing. Basically, it tells us it's three arrays that are sort of a sparse way of encoding the result. It tells us for each input how many things are associated with the result and what is the start index of each thing. So it's three arrays. It gives us the actual indexes as well as the number of results and the offset to the first result. So we pass those in to our BBH tree. We give it our bounding boxes for the queries, and we call this find bounding boxes function, which gives us the number of results. Here's sort of a nice thing in our Axom array class. We could, instead of allocating space for each entity on the device, which we're immediately going to overwrite, we have a way of telling it, I'm giving you memory, it's uninitialized, but we're expecting you to initialize it later. So this just saves some effort by passing in this Axom array uninitialized. Let me undo that. Okay, so what do? We okay. Sorry, I got lost for a second. We first call this BVH and where is it? Find bounding boxes. That gives us the candidates that we would actually need to check with the lower level function later. So that's a way of filtering out the initial candidates. But then once we have those candidates, we call the kernel that actually checks for the intersections. So this sort of looks like the previous example. We do this thing with Raja atomics to atomically add things. I missed the point before where we use the number. Okay, this is the part I was missing before. So given that previous BVH test, that tells us how many possible candidates we have, how much space we need to allocate for the possible candidates. So we create an array that's initialized to that proper size. So we don't have to do two passes this time. We already have an estimate that's conservative on the number of results we're going to have. So we allocate that space. And then this time when we call our Rajified kernel, the Axom for all, which is a wrapper around Raja for all, we directly add the candidates we find using Raja atomic add. So we basically we figure out what. Let me take a step back. For each intersection we find, we get a unique space for that using this atomic counter. Basically, it tells us this is the index that this candidate pair can write into, and then we store the indices of the triangles that intersect. And then the last thing we need to do here, once we have this array on the device, is we need to write it back to the host. So I'm a little confused why there's two of these. Maybe I was looking at the wrong thing. Oh, yeah. Okay. I skipped a step. What we're actually doing is we have this array in our CSR representation, which is for each input triangle, we have a list of output candidates, and that's in the CSR array. So that's a bit awkward to deal with on the GPU because we don't want to sort of loop over this ragged array and have different amounts of work per kernels. So what we do is we take this ragged array and we turn it into corresponding arrays of indices and candidates. Um, so it just it puts it in a form that's better for operating on the GPU. Um, it's basically two arrays that we could just directly iterate over, and that's why this uh, final Axom for all um, is very simple because it just goes over the number of candidates. Our initial index is in the indices array at index I, and the candidate we're checking is in the candidates array at index I. And then we call Axom primal intersect on the two triangles. And if they do in fact intersect, we add them. So sorry about that confusion there. It's it's a, a form that works really well with our kernels to set up on the GPU. So I think if I run that again on our Porsche model, which has 150,000 triangles, we could see, this time I ran it with dash V to be a bit verbose. It's checking self-intersections. The input mesh has 150,000 triangles. If we looked at all the pairs, that would be 11.5 billion triangles that we would need to check. But when we ran it through our BVH tree, we filtered that down to a very small subset of that, only 3 million candidates that we needed to check instead of 11 billion. So, 3 orders of magnitude, maybe 4. Those were the candidates. And then after we filtered it to check which ones actually might intersect, we went even further to half of that, to 1.5 million. In the end, this model, which we showed here, had 9,479 triangles pairs of triangles that actually intersect. These are the red ones. And our algorithm found those, and it did that on the GPU in like a quarter of a second or so. If I ran that same model on the CPU, so that's the sequential, we see that our spatial index made this algorithm fast enough to run really well on the CPU. It took, let's see, it took 0.08 seconds to initialize the BBH, and then to get the candidates took about half a second, and then to remove the invalid candidates, it took 0.0275 seconds, and then the actual intersections took 0.12 seconds. So that was on the Porsche model, which had 150,000 triangles. If we run that on the car model, it takes longer, but it's still a reasonable amount of time. It took 1 second to initialize the tree, 6 seconds to check the candidates, and then I lost my window. About, another 2 seconds to filter and find the actual candidates. So, okay, so what's our takeaway here? Axom is a library. It's open source on GitHub. Its purpose is to have computer science infrastructure in support of HPC simulations. And a big portion of Axom relates to computational geometry and spatial queries, but we also support other things that are common, like logging, dealing with input for simulations, dealing with checkpoints and restarts. and I'm probably leaving out a bunch of other things we do, but for this library, we have our intention is to run on all of the big supercomputers we care about. Some of them are CPU based, some of them are GPU based. They support different vendors, NVIDIA and AMD. We went through a tutorial that solves a very important thing for us, which is checking if input meshes we get from users for some applications are valid. We actually created this because users were giving us meshes that were not valid, and this was helpful through debugging for telling them, hey, your mesh is not valid, go back to your mesher and create a better mesh. And also to sort of, help us visually see where the problems in meshes are, and maybe do some simple mesh repair, things like that. We started with a very poorly performing algorithm because it checked every pair of triangles. Then we said, hey, let's port this to the GPU. And we got a huge speed up there, but it was still not a great algorithm for our purpose, or not the best algorithm. And then using some additional insight and very standard tools from computational geometry and computer graphics, and those related fields in CAD, we were able to come up with a better algorithm that uses spatial indexes that are built into Axom and solve the problem a lot faster using the available devices, either CPUs when it's available, OpenMP when it's available, CUDA or HIP when they're available. So that wraps up our tutorial. Are there any questions people have or want to ask? Yes, great question. Are there other examples demonstrating other capabilities in Axom? So that was our tutorial. We have some other parts of Axom. Let me make this a little bigger. So Axom source tools. We have several tools in Axom. The mesh tester is sort of the example we were working through. We built up some of its capabilities, but if you run, if you look in an installed copy of Axom, there's a bunch of examples that we generate, like binaries. This is one of them, which checks for the self-intersections and does some other work. It also checks like topological information about the mesh and the number of connected components, I think. We have some other examples. This one's called Convert CIDR Protocol. So CIDR is this simulation data, like key value pair that has like meshes and fields and things like that. It writes out into an HDF5 format, which is like a binary format. This Convert CIDR protocol is a way of like converting it to other protocols that are maybe more human readable if we're trying to debug things. We have this new capability that was added very recently. So one of the things we do in Axom is set up initialize volume fractions in multi-material simulations. That's where we're running a simulation on different materials, maybe like water and air and rubber, or whatever. But the contours of the materials that we're operating on don't align with the mesh cells. So we have this process that we call shaping or painting or volume fraction initialization, depending on what your background is. And that sort of supports bringing in these contours and shaping them onto a simulation mesh. This example here is a Python script that reads in SVG images with curves and circles and ellipses and things like that, and turns it into a format that we could read into our application, the MFEM NURBS mesh format. And then in Axom Quest, examples, here's where we have a lot of different examples of Axom's capabilities. We have this winding number application, Quest winding number, which loads in that SVG file converted to a NURBS mesh, and it could shape it into a computational mesh. So it creates these volume fractions for us. We also have, let's see, what else do we have? We have a Delaunay triangulation in 2D and 3D. So given a set of points, it turns those into a Delaunay triangulation. So it creates a triangulation with certain properties of that point set. Our scattered interpolation example takes that set of points, converts it to a Delaunay mesh, and then allows you to do interpolation on those points. Thanks, Brian. Brian just pointed to this directory, or to the built version of these examples. So scattered interpolation is given a point set with fields associated with it, we want to interpolate values at arbitrary points. So it uses a Delaunay mesh for that. We have a signed distance example. So given an STL triangle mesh and a set of points, it computes the signed distance. So that's the closest point from the query to the surface, as well as whether it's inside or outside. We have a similar one with in-out that doesn't do signed distance. It just tells you, is this inside or is this outside? Another cool example we have is Quest distributed distance query. So this one is where we have a collection of entities that's distributed across our MPI ranks. And then we have a collection of other points that's also distributed, but not necessarily in a coherent way with the first one. And it wants to check for every point in the query, what's its closest point in the object. So basically it's closest point for two collections of points, but they're each using different MPI decompositions. So it does a lot of it moves points in an intelligent way to be able to find which point in the point set is the closest one and what MPI rank does that live on. We also have marching cubes built in. So given sort of a mesh with some fields, create an isocontour. And then this point and cell is given a mesh, it could be a high order, like finite element mesh, and a collection of points. We want to figure out which cell contains the query points and what are the parametric coordinates of the point within that cell. So that's used for like tracking points to cells in a mesh, like a point and cell sort of model. Other questions? It looks like our tutorial time has officially ended. I could definitely stay around to field some questions. I wanted to thank everyone for participating in this tutorial. And if you have feedback for us, we'd love to hear it. Things you'd want to learn about Axom, things we didn't cover, things, sort of other topics, things like that. Yeah, so that's a great question, Ma. Are there any multi-physics applications developed by Axom? Where to find them? So there is GitHub. There's an engineering code that started up not too long ago. Here, I'll post this link. So it's like a next gen engineering code at Lawrence Livermore. It's a thermomechanical simulation code that's based on high order finite elements. It uses MFEM for its meshes and finite elements, and it uses Axom for a lot of its capabilities. So it has a lot of the things we talked about. It has checkpoints and restarts. It uses inlet for parsing input to the simulation. It uses Slick for logging. There's probably other things I left out. Just to add some other examples, we have a library called Tribal, which is a contact mechanics library. So that's where you have sort of two entities that are in some sort of proximity, and you want to compute the contact forces that they have, and as well as sort of like, what direction they're moving to maintain momentum, to conserve momentum. And that uses Axom's spatial indexes for finding which pairs of entities might be close to each other, as well as some other functionality, computational geometry, and things like that. So I'll post a link to Tribal as well. And someone else asked about checkpoint restart. There's a library called Spheral, which is smooth particle hydrodynamics. It also incorporates some of Axom into it. So definitely feel free to check there.